So today we are going to start with the next chapter called as thermodynamics. So now if you just read the name thermo and dynamics, you come to know about what are we going to study in this chapter. Okay, so thermo means what? Thermo means heat, dynamics means motion. So we are going to study about the motion of heat. Okay, so that means heat will flow from where to where. Okay, that we are going to study in this chapter. So thermodynamics, it is the branch of physics that deals with the heat and temperature. Okay, it deals with the study of heat and temperature. And we all know that the heat flows from a body which is hot to a body which is cold, right? From hot body to cold body. So then, now there is some nomenclature in this chapter which we need to understand. So the first thing is system. So now what is system? So now there are a lot of things in the surrounding, right? I mean, there are a lot of things in the universe, and then we are interested in the properties of a particular thing. So suppose you take tea in the thermos, or suppose you take a cup of tea. So that cup of tea is your system. Okay, so it's the region of space whose thermodynamic properties are of interest, right? So you want to understand, you want to study properties of a particular thing, right? Particular part of the whole universe, that is called as the system. Okay, so it's the region of space whose thermodynamic properties are of interest. And what is surrounding? So everything apart from the system, it is called as surrounding. So everything not included in the system but can affect its thermodynamics properties is known as surrounding, right? So remaining part of the universe, you can say, it is called as surrounding. So then there are three kinds of system. One is the open system, then there is a closed system, and then there is an isolated system. So what is an open system? So if we take this example, suppose take a cup of tea. So what can happen here? So the energy as well as matter can go out of this system, right? So you can sip the tea, so matter can go out, and the energy means the heat can flow out. If it is at higher temperature, then the heat will flow from the system to the surrounding. If it is iced tea, then what will happen? The heat will flow from surrounding to the system, right? So cup of tea is an open system. So what is an open system? Energy as well as matter can be exchanged with the surrounding. Then there is a closed system. Okay, so suppose this is a tin, and okay, this container is made up of some metal, and there is some ice in this container. So this is a closed system, right? This is an example of a closed system. Okay, then here what can flow out? Energy can go out. Okay, energy can move to the system or away from the system, that means from system to surrounding or from surrounding to system, but the matter cannot go out. Okay, so this is known as a closed system, right? And then next is an isolated system. So this thermos flask. Okay, so suppose there is some tea in this thermos flask. So this is an isolated system, right? Because energy as well as the matter, they cannot go out. Okay, so this thing is clear. What is an open system? Energy as well as matter can be exchanged between the system and surrounding. Closed system, only the energy but no matter can be exchanged. And isolated system, neither the energy nor matter can be exchanged. Okay, are these definitions clear? Yes, no? All right, good. Okay, so in last chapter we studied about the pressure, okay, as well as the internal energy. So we studied about the kinetic theory of gases. That pressure is because of what? The velocity of molecules, and temperature is also because of what? Velocity of molecules, right? So suppose you take this container, and there are n number of molecules of a gas inside this container, and they constantly collide with the walls of container. So when they collide, what happens? They exert pressure or they exert force on the walls of container, and that force per unit area gives rise to the pressure. Okay, that is pressure due to the gas. Okay, and so these molecules, because they are moving in random directions, so they have certain energy. So that energy, their kinetic energy, it gives rise to the temperature, or the amount of energy is actually the temperature, right? We have studied this, that U is equal to 3 by 2 nRT. If there are n number of moles of a monoatomic gas, then its internal energy is equal to what? 3 by 2 nRT, right? So now see, there are two kinds of properties of a system, or two kinds of variables you can say. So what are two kinds of variables? One is the microscopic variables and one is macroscopic variables. Okay, or microscopic properties and macroscopic properties. So now microscopic is clear, right? So if you look into the system, what is the velocity, what is the kinetic energy of each and every molecule of the system, those are microscopic quantities, right, or microscopic properties you can say. But what is macroscopic property? So suppose the temperature of the system, the volume of the system, mass of the system, these are macroscopic quantities. Okay, so the quantities which are related with the amount of substance, right? So those are, macro means bulk, the properties of a bulk system. Okay, these are macroscopic quantities, right? So now a system is said to be in the thermodynamic equilibrium when its macroscopic properties, macroscopic properties means variables like the temperature, volume and pressure, etc., do not change with time. Okay, if temperature, volume, pressure, mass, etc., these things, they do not change with time, then the system is said to be in thermodynamic equilibrium with the surrounding. Okay, not any mass goes out or comes in the system. Okay, there is no exchange of mass, there is no exchange of temperature, sorry, on the heat, right, or the volume doesn't change, right? So then the system is said to be in thermodynamic equilibrium. Okay, so this is thermodynamic equilibrium. Then there are some properties, some are intensive properties and some are extensive properties. So intensive properties means what? They do not depend upon the size of the system. Okay, size of the matter in the system. So what are they? The density, pressure, temperature, these are intensive properties, or you can say boiling point. Okay, so boiling point of a system is, suppose for an example you take a cup of water. Now if you take cup of water or you take mug of water, the boiling point of water is same, right? Okay, its density would be same, right? The pressure that it exerts, it also is same. Okay, so these are the intensive properties, and extensive properties are, they depend upon the amount of substance, amount of matter. So that is mass. Mass is an extensive property. Okay, it's volume. Volume is an extensive property. Okay, so this thing is clear. Intensive and extensive. Yes, no. Okay. After that, let's talk about internal energy. Now, what is internal energy? So, energy which is due to the internal motion. Okay, it does not depend on any external thing. So, for an example, suppose you take again some container and there is some gas inside that container. What do the gas molecules do? They constantly move in random directions, right? So the energy due to motion of these particles which are inside of the system, that is internal energy. So we have studied this in kinetic theory of gases. So what can these gas molecules do? They can move in random directions, okay, in x, y, z directions. So if it is just monoatomic gas, it can just move in random directions. Okay, so it can have some kinetic energy because of that. Then if it is a diatomic gas, then what else can it do? It can rotate. Okay, and at higher temperatures, what else can it do? So it can vibrate also. So energy, because of all of these motions, different degrees of freedom of a gas, okay, these are internal degrees of freedom, right? So it is the internal energy, okay, it has nothing to do with the surrounding, okay, nothing to do means it's because of the internal motion only, okay. So internal energy of system is the sum of potential energy and kinetic energy of all molecules of the system, okay. Simple definition, it is just sum of the potential energy and kinetic energy of all molecules of the system. And we had studied this in kinetic theory of gases, that for 1 mole of a monoatomic gas, U is just equal to what? 3 by 2 RT. Okay, for 1 mole of monoatomic gas, U is just equal to 3 by 2 RT, right? So that is internal energy. After that, let's talk about the zeroth law of thermodynamics. Now there is a story behind this, that why is it called as a zeroth law. So the reason to that is, first law of thermodynamics was developed, then the second law came, okay, and after that some law was discovered, this law was discovered, and which is actually very basic in nature, okay, it's more basic compared to that of the first law and second law, and that's why it was named zeroth law, right? So this law is very simple, and you might say this is a common sense, okay. So it states that two systems are in thermal equilibrium with the third system, then all three are in thermal equilibrium with each other, okay. Two systems are in thermal equilibrium with the third system, then all three are in thermal equilibrium with each other. So for an example, suppose we have these three systems that you can see here. There are adiabatic walls. So this is an adiabatic wall, this is a diathermic wall. So now what is an adiabatic wall, what is a diathermic wall? So adiabatic means the heat cannot be exchanged, okay. Adiabatic wall means the heat cannot be exchanged between the two parts. So suppose two parts are separated by an adiabatic wall. Adiabatic means insulated, okay, there cannot be a heat exchange. And diathermic means what? The heat can be exchanged, okay. So adiabatic means there cannot be heat exchange between the two parts which are separated by that wall, and diathermic wall means a conducting wall, so there can be a heat exchange, okay. So suppose you have, this is system 1, this is system 2, right, and this is system 3, and U1, V1, N1 are what? The internal energy, the volume, and the number of molecules of the system. U2, V2, N2 again internal energy, volume, and number of molecules of this system, and U3, V3, N3 internal energy and the number of molecules of system 3, okay. So now what you are doing, so first and second system, they are separated by an adiabatic wall. Adiabatic means there won't be any heat exchange between the first and second, right? Then these two are separated with the third system by a diathermic wall. That means there can be heat exchange between first to third as well as second to third, right? So after some time, what will happen? Can you tell me what will happen after some time? Diathermic means wall, means what? It's a conducting wall. Suppose this one is at higher temperature compared to first and second. So after some time, what will happen? If this is at higher temperature, this one and this one, they are comparatively at low temperature, then some heat will flow from system 3 to the first system and second system, right? And it will keep on flowing till the time temperature of system 3 becomes equal to that of temperature of system 1 and temperature of system 2, okay, right? So temperatures become equal. After that, suppose you remove this wall, suppose you have some kind of button, okay, you press that button and this adiabatic wall becomes a diathermic wall, and this diathermic wall becomes an adiabatic wall, right? So you leave the system for some time. So now we have discussed that what will happen, their temperatures will become equal. and if temperatures become equal, then now what here, what can we say here? The system 1 and system 3, they are in thermal equilibrium with respect to each other. System 2 and system 3, they are in thermal equilibrium. Okay, but can we say the same about system 1 and system 2? So Zeroth law of thermodynamics says that yes, they will be in thermal equilibrium. Okay, so if you change this adiabatic wall to diathermic wall, what will happen? Nothing will happen. Okay, whatever is temperature of system 1, okay, it remains the same, right? And temperature of system 2 will remain the same because they have already attained the same temperature by means of system 3. Not directly, there was no direct heat exchange between the system 1 and 2, but still by means of system 3 they have attained equal temperature. Okay, so this thing is clear. Alright, so this is zeroth law of thermodynamics, that if the system 1 and system 3, they are in thermal equilibrium with each other, system 2 and system 3 are in thermal equilibrium, then the system 1 and system 2 have to be in thermal equilibrium. Okay, so this is just like if A is equal to B, B is equal to C, then A has to be equal to C. Okay, alright, so this is simple. Then let's talk about the next law, which is the first law of thermodynamics. Okay, first law of thermodynamics. So what does it say? It says that the amount of heat supplied to the system is equal to the sum of work done by the system over the surrounding, okay, and change in internal energy of the system, right? So let us understand this. So suppose you have, our system would be simple. Suppose there is some gas in this container and there is this piston. Okay, there is this piston, right? So this is surrounding. Okay, this is surrounding, and now you are supplying some heat. Okay, you are supplying some heat. So either the heat can conduct from surrounding to the system, or you are separately giving some heat, suppose, and you can measure that heat. So then what will happen? Once you heat the system, that means the gas molecules, then the energy of the gas molecules will increase. So suppose initially they were moving with some velocity, okay, so their average velocity was 20 meters per second, then it might happen that their velocity will increase to 25 meters per second or 30 meters per second, average velocity, right? So their kinetic energy would increase. That would be the first thing. What else can happen? Because of this increased energy, this piston would be lifted up. So suppose there is no extra pressure, there is no excess pressure, the pressure of the surrounding, that means the air pressure and pressure inside the system would be equal, right, before you give any heat to the system. Now suppose you give some heat to the system, what will happen? The pressure, the energy of these atoms will increase, and we have seen in the kinetic theory of gases there is direct connection between the energy and pressure. So that means what will happen? The pressure will also increase. So pressure increases, that's why the piston will be lifted up, and if piston is lifted up, some work is done. Why? Because the volume will increase. Okay, piston is lifted up, that means there is displacement. So if there is displacement, there is some work done, right? So now the energy given by the law of conservation of energy, we can say the energy given is equal to what? Its internal energy, rise in the internal energy plus the work done, amount of work done. Okay, so this is very simple. The amount of energy given, heat energy given, is delta Q. The heat energy that flows from the surrounding to the system, it's delta Q. It is equal to delta U, that is rise in the internal energy, plus delta W. Okay, delta W is the work done, right? So work done, if the pressure of the surrounding and system is equal, okay, then work done can be just written as P delta V. Okay, the work done can be just written as P delta V. Otherwise, if the pressure is not constant, pressure changes, then we need to find out work done by this method. Work done would be what? The integral from V1 to V2 of P dV. Okay, so we'll talk about this later. The work done is equal to what? P delta V. So this thing is clear? Yes, no, everyone? Okay, till this point, that amount of energy given is equal to what? Increase in the internal energy plus some work done against the surrounding, right? Now, is there any confusion that in chemistry there is some negative sign here, something like that? Is there any confusion like that? Yes, no? I have heard this thing in past that, okay, this formula, it's not same. There is a confusion? Alright, so there won't be any confusion. See, look at it this way. The amount of energy given, it is utilized in two ways. In raising the internal energy and in doing some work, right? The amount of energy given to the system, it is utilized in two ways. One is in raising the internal energy of the system and doing some work against the surrounding. Okay, so then you can say that some x amount of energy is given, right? Part of that is used in increasing the internal energy and part of that is used in doing some work against the surrounding. Okay, so this is simple, right? Yes, no? All right, so then see, work done by the system and on the system, right? Which one would be positive work, which one would be negative work? Let's understand that. So simply in this formula, okay, as we have written this formula, this work done is the work done by the system on the surrounding. Okay, this is work done by the system on the surrounding, right? So see here, these are molecules of the system, okay, and these walls are rigid. These walls are rigid, but this piston is not rigid in the sense that the piston can move upwards or downwards, right? And now see, these molecules, they will constantly collide with the walls of container and also on this piston. So if they collide on the container, or sorry, they collide on the piston, that means the force exerted by them would be in upwards direction, right? Force exerted by them is in upwards direction. Okay, so surrounding has air pressure, there is air in the surrounding, so it exerts pressure in downwards direction, right? Pressure is exerted in the downwards direction, okay, on the piston, right? So then surrounding exerts a force in downwards direction, system is exerting a force in upwards direction. If this piston is lifted up, that means it is moving in direction of the force exerted by the system. That means work done by the system would be positive work and work done by the surrounding would be negative work. Okay, so if the piston moves outwards, work done by the system would be positive work, right? And work done by the surrounding would be negative work. Okay, then so this is written in different ways. Sometimes they say work done by the system, sometimes they say work done on the system. So on the system means it is work done by the surrounding, right? So if the piston moves down, then work done on the system would be positive because it is work done by the surrounding, right? So because if piston moves down, then the displacement is in direction of the force exerted by the surrounding. Okay, that is displacement is in direction of force exerted on the system, and that's why the work done would be positive work. Okay, right, work done on the system would be positive and work done by the system would be negative. Is this thing clear? Positive and negative, everyone? Okay, what sign will you take positive in this formula? Suppose the piston goes up, piston moves up, right? If volume increases, simply if volume of the system increases, then the work done would be positive in this formula. and if volume of the system decreases, then work done would be negative. Okay, this thing is clear? All right, good. So then now see, we know that the pressure exerted by the system, okay, pressure is force divided by area. Okay, force exerted by system, that means these molecules on the piston per unit area of the piston, that is called as pressure. So then you take that area on other side, so force can be written as what? Pressure times area. And then suppose the piston moves by a very small amount dx. Okay, piston moves by a very small amount dx. Okay, then the work done in this process can be written as what? F times dx, that is F can be written as what? P times A. Okay, F can be written as P times A. So therefore work done is equal to what? P times A dx. And what is A dx? So A is area of this piston, dx is the change in, or dx is the displacement. That means A times dx is what? It is this much volume. Okay, it is increment in the volume, and therefore work done can be written as what? Small work done can be written as P dV. Okay, small work done can be written as P times delta V or dV you can say. Okay, so that is P times change in volume, right? And then now whether the pressure is constant, whether the pressure is not constant, see the work done in changing the volume from V1 to V2 can be written as what? It would be just integration of this work done. Okay, it would be just integration of this work done, right? So suppose the volume changes, so as it is written over here, okay, total work done when the volume changes from V1 to V2, total work done for change in volume from V1 to V2, okay, can be written as what? It is just equal to the integration of P dV, right? It would be just integration of the small work done, okay, from V1 to V2, right? It would be integration of small work done from V1 to V2, okay. And we know that integration is area under a curve. Okay, we know this thing that integration is what? It is the area under a curve. So therefore what would be the work done? Let's say here the pressure is something and volume is something. Volume is V1. Okay, here the volume is V2. Then how much would be the work done? Work done is just the area under this curve, PV curve, right? Just like work done is what? Area under the force versus displacement or force versus distance curve. Okay, so just like that, the work done here would be what? Area under the pressure volume curve. So that is this area. Is this thing clear, everyone? All right. Now shape of this curve would be different in different cases. Okay, and we are going to learn about the thermodynamic processes. So in different thermodynamic processes, the shape of this curve would be different. That means the work done would be different. Okay, so let us see this question based upon the first law of thermodynamics. The internal energy change in the system that has absorbed 2 kilocalorie of heat and done 500 joule of work is. This is very simple. Tell me, 2 kilocalorie of heat is absorbed, so delta Q is equal to 2 kilocalories. Okay, and all of the options are in joules, so that means we need to convert this to joules. So we know that 1 calorie is equal to what? 4.2 joules. Okay, so this is equal to 2 multiplied by 4.2 multiplied by 10 raised to 3 because this is in kilo, okay, kilocalories. So this will be 8400 joules, and it has done some work, so 500 joule of work. That means what would be the change in internal energy? So this is very simple. So let's write down the formula. So delta Q is equal to delta U plus delta W, and therefore what is delta U? So delta U is just delta Q minus delta W, okay, and let's read this. And it has done, okay, the system that absorbs this much heat and does this much work. So this work done would be positive, right? The work done would be positive, okay, so delta W is positive. So therefore what is delta Q? It's 8400 minus, it is 500, okay, so 8400 minus 500 is what? 7900, okay. So this is from 2009 and very simple question, right? Okay, is this thing clear? All right, very simple question. Let's see next one. 110 joule of heat is added to a gaseous system whose internal energy is 40 joules. Then the amount of external work done is, tell me. Okay, so in original question, it's not 110 joule of heat is added to a gaseous system whose internal energy is 40 joule. The question is not this way. The question is like this. Question is which acquires, okay, which acquires an internal energy of 40 joules, then the amount of external work done is. Then it's very simple, right? So that was a misprint, okay. Then you have delta Q is equal to delta U plus delta W, and that is what? 110, and delta U would be equal to just 40 because it acquires 40 joule of energy, and then work done is just equal to what? 70 joules. Okay, so that is the answer, right? This one is clear, everyone? So very simple one. Let's see next one. First law of thermodynamics is consequence of conservation of. Again, this is very old, but it can be asked. Tell me. Option B, everyone. It is consequence of the law of conservation of energy, right? Very simple. Okay, good. Then I guess we'll need to understand more. We'll need to learn more to solve any of the other questions, right? So let's go back to the theory. Okay, so now let's understand another thing which is called a state variable and path variable. So now what are state variable? So see, the macroscopic variables, pressure, volume and temperature, etc., they define thermodynamic state of a system. Okay, the values of macroscopic variables at some time, it defines thermodynamic state of a system. Okay, so let's understand it here. Suppose there is some system, okay, and it has pressure P1, volume V1 to start with, and now suppose it expands. Okay, so we can consider this gas. Suppose it expands. So initially there was pressure P1, its volume was V1. Initially it was at pressure P1, volume V1, and it expands to volume V2, and pressure at that time is suppose P2, right? So now it can go from pressure P1, volume V1 to pressure P2, volume V2, let's say along this path. That means the pressure and volume can change this way Okay, it can change this way or it can change this way. Okay, there can be numerous ways in which the pressure and volume can change, right? The graph between pressure and volume connecting these two states, it can be this one, or this one. From the first law of thermodynamics, what I can say is delta Q. Delta Q is what? It is the amount of heat energy taken by the system, absorbed by the system, or given away to the surrounding by the system. Okay, so delta Q is equal to delta U plus delta W. This is our first law of thermodynamics, right? Delta Q is equal to delta U plus delta W, and then now delta U is what? So we know this, that PV is equal to nRT, okay, and U is equal to N times CV into T. So we had seen this in last chapter, okay, kinetic theory of gases, that internal energy of a system is equal to what? N times the number of mole times the CV, means the specific heat capacity at constant volume times temperature. Okay, this thing is clear? Yes, no? Okay, so U is equal to N times CV into T, right? For monoatomic gas, it is equal to, you can say, N times 3 by 2 R into T. For diatomic gas, it is equal to N times 5 by 2 R into T, right? We had seen this thing in kinetic theory of gases. And what is that 3 by 2 R, 5 by 2 R? It is CV, specific heat capacity at constant volume. Okay, so then now see, from this ideal gas law, what you can say is temperature is equal to, okay, move that nr on other side, so it is just equal to PV divided by nr. Okay, it is just equal to PV divided by nr. N can be cancelled out and U can be written as what? CV, okay, which will be a constant, specific heat capacity times PV divided by R. Okay, specific heat capacity times PV divided by R. Okay, and now suppose when the system goes from state 1 to state 2, it moves from, suppose, pressure volume P1 V1 to pressure volume P2 V2, then the change in internal energy, okay, what would be the change in internal energy? The change in internal energy would be, see, CV divided by R is a constant, then what you can just say, that final pressure volume, okay, P2 V2 minus P1 V1, okay, because U is equal to CV by R times PV. Okay, so change in U would be equal to what? U2 minus U1. So U2 would be equal to CV by R times P2 V2. U1 would be equal to CV by R times P1 V1. So change in U would be just equal to what? CV by R times P2 V2 minus P1 V1, and this is a constant. Okay, so this is a constant, means okay, so for same pressures and volumes, okay, same starting and end point, you can say same start point and end point, this thing is a constant. So change in internal energy is a constant, so it does not depend whether the system goes from here to here along this path 1 or from the path 2 or the path 3, right? Okay, so if a thermodynamic system goes from some initial state, so here you have some values of P1, V1, T1, okay, and to some final state. So thermodynamic state is defined by macroscopic variables, pressure, volume, temperature. So P1, V1, T1 to P2, V2, T2, okay. So then the quantities that do not depend upon the path taken, they are known as the state variables, and the quantities that do depend on the path taken, they are known as path variables. Okay, so now state itself is defined by pressure, volume, temperature, okay, and therefore what we can say is pressure, volume, temperature, they are what? State variables, okay, as well as the internal energy. So we have seen this, the change in internal energy would be constant and it will not depend upon the path followed, and that means, okay, that means the internal energy is also what? The state variable. But then the work done and the amount of heat absorbed, they are not state variables, they are path variables, because for all these paths work done would be different, right? So now just for an example, suppose this is the initial state P1 V1 and this is final state P2 V2. Okay, so these three curves, path 1, path 2 and path 3, I have drawn over here. Okay, so now this is P1 V1, of course this is P2 V2, again this is P1 V1 and this is P2 V2. So you can see here work done along the path, this path 1 would be more compared to that of work done along path 2 compared to that of work done along path 3, right? Yes, no, this thing is clear, because we know work done is equal to what? The area under pressure volume curve. So now for the same start point and end point, work done along this path would be more compared to that of work done along this path, and it would be more compared to work done along this path, right? So work done is path dependent. Okay, even if the initial and final pressure volume values are same, for all three cases work done in first case would be more than work done in second case, and it would be more compared to that of work done in third case. So work done depends on the path followed. Okay, right? But then work done depends on path followed, internal energy it does not depend on the path followed, so that means the delta Q will depend on the path followed. Okay, so this thing is clear, everyone? Right? State variables means their values. So suppose you take first state and initial state and final state, so along the paths, along the different paths, the state variables will take different values, but their starting values and end values, they do not depend on what path is followed, right? Okay, so pressure, volume, temperature, and of course since internal energy also depends on temperature, or you can just say that even if we don't see this derivation, we can just say that internal energy is directly proportional to temperature, and pressure, volume, temperature define a thermodynamic state. Therefore the internal energy is also what? A state variable. Okay, internal energy is also a state variable, but the amount of heat absorbed or given away and the work done, these are not state variables, they depend on the path. Okay, they depend on the path followed. So this thing is clear, state variables and path variables, everyone? Yes, no? Okay, so what are state variables? The thermodynamic variables which are path independent, they are called as state variables. So internal energy, pressure, volume, temperature. Path variables, the thermodynamic variables which are path dependent, are called as path variables. So heat and work are path variables. Okay, so there can be direct question based upon this state variables and path variables. Okay, then let's talk about the thermodynamic processes. Okay, let's see thermodynamic processes. So first one is quasi-static process. So what is a quasi-static process? Quasi-static means a process which happens very slowly, infinitely slowly. Okay, but that's not all. In quasi-static process, what else happens? The system and the surrounding, they are at equilibrium throughout the process. Okay, they are at equilibrium throughout the process, right? So that is a quasi-static process. Okay, so for an example here, okay, let's consider again the same thing, same diagram. So you have this gas contained in the container and there is this piston. So now piston is just left over that gas. Okay, it is just kept, right? It is just kept. So then the pressure of the gas and pressure of the surrounding would be equal. And now suppose you start giving some heat. So you are giving the heat to this system very slowly, so that you give the heat, there would be slight difference in the pressure, because when you give the heat, pressure would increase slightly, suppose, and when pressure increases, then what will happen? As soon as pressure increases a little bit, the piston is lifted up, right? But because you are giving heat very slowly, then what will happen? The piston will be lifted up, okay, and instantaneously the system and surrounding, they will again come back to the equilibrium. Okay, this thing is clear. Suppose, for an example, 100 molecules are colliding with the piston, and that defines 100 molecules are colliding with the piston per unit time, okay, and they maintain pressure equal to pressure of the surrounding, right? Now suppose they are colliding with 20 meters per second on an average. Now you give energy, okay, you give heat to it, and their speed increases slightly, it becomes 20.1 average speed, okay. What would happen? The pressure would increase, right? So pressure increases, and then the piston is lifted, but piston is lifted so slowly that now pressure has increased very slightly, okay, and piston is lifted, so that the pressure of the system and pressure of the surrounding again comes back to what? Equilibrium, okay. There is slight mismatch, and again it comes back to equilibrium. So that is quasi-static. Quasi-static means at all points the system and the surrounding, they are in equilibrium. Is this thing clear, everyone? Right, at all points the system and surrounding would be in equilibrium, okay. So this kind of process can be reversed, okay, this kind of process can be reversed, and the system, if it is not in equilibrium with the surrounding, then the process cannot be reversed, okay. In that case the process would not be reversible, right? For an example, suppose you take a balloon, okay. Now the balloon is inflated, and suppose you just release it, okay. So it is tied, there is a knot tied to a balloon, you just release that knot, then what will happen? The air will come out of the balloon. Now you cannot take same air, okay, and inflate the balloon again. This process is not reversible, right? So this is not quasi-static too. Quasi-static means steady, right? So the system and surrounding, they will be constantly under the equilibrium. This thing is clear? Okay. All right. So all processes that you are considering now, the isothermal process, will consider isothermal process, isochoric, isobaric, and adiabatic process. So all of them, they will be quasi-static processes. Okay. So now what is an isothermal process? So let's see the definition. A thermodynamic process in which the temperature of the system remains constant is called as an isothermal process. Very simple, right? So it will always follow PV equals to nRT, because temperature is constant, okay. All right, so what did I say? PV equals to nRT, okay. It will, this is ideal gas equation, it will be followed anytime, okay. So here the temperature is constant means PV is constant, right? Temperature is constant means what? PV is constant, okay. So in isothermal process, what will happen? The temperature of the system will remain constant throughout the process, okay. So whether the gas expands, whether the gas compresses, okay. So that means, see here, what is an isothermal process? So if walls of the container are conducting, walls are conducting means they are diathermal, then the process is isothermal. Okay, so suppose you are giving some heat to this system, then what will happen? So the temperature of the system will rise. Okay, but then you are giving the heat very slowly. Whatever is increment in the temperature, now the heat will flow out from the system to the surrounding, and again the system means this container, gas in the container, it will come back to the same temperature as that of the surrounding, and it will happen very quickly, right? Instead of saying very quickly, I should say this will keep on happening continuously. Okay, so this is a quasi-static process. Both things here, see, if you give heat, what will happen? The temperature will rise, the pressure will rise, so the system comes back to the equilibrium with surrounding very quickly, or the equilibrium stays. Okay, so you give some heat, pressure will increase, so the piston is lifted up so that the system and surrounding are at same pressure. Okay, you are giving some heat, temperature increases, but then the heat flows out of the system to the surrounding, so that again they come to what? The equilibrium. That means the temperature of system and surrounding would be equal, right? Because the walls are conducting. So this is a quasi-static isothermal process. Is this thing clear, everyone? Okay, all right, good. Then all processes are quasi-static only. Next is isochoric process. Okay, isochoric process. So now in isochoric process, what do you mean by isochoric? Isochoric means the volume will remain constant. Okay, the volume will remain constant. There will be no change in the volume, right? So no work is done by the system on surrounding, right, and by the surrounding on the system. So we have taken example of this gas in a container. No work is done by the gas on the surrounding or by the surrounding on the gas. So this is an isochoric process. The volume remains constant. Okay, so work done is equal to 0. That means what will happen? If work done is 0 and you're giving some heat, if work done is 0, you're giving some heat to this system. So where is the heat utilized? Only in raising the internal energy of the system, right? If work done is equal to 0, where is the heat utilized? Only in raising the internal energy of the system. Okay, because just apply the first law of thermodynamics. Work done is equal to 0 because change in volume is equal to 0, and then delta Q is equal to what? Delta U plus delta W. Delta W is 0, so just internal energy of the system will change, right? So this is an isochoric process. Okay, so in isochoric process, all the heat is utilized in changing the internal energy of the system. Okay, next one is isobaric process. So now what is an isobaric process? All right, before that, if we see the pressure versus volume graph of this isochoric process, how will it look like? For any isochoric process, since volume remains constant, okay, pressure can change, the volume remains constant, right? So the pressure volume graph will be a straight line like this. Okay, volume remains constant, V naught, let's say. To start with, the volume was V naught and volume remains V naught. Okay, this is clear. This is an isobaric process. Okay, in an isobaric process, what happens? The pressure remains constant. Okay, in isochoric process, volume remains constant. In isobaric process, see here, one of the units of pressure is bar. Okay, 1 bar, 2 bar, etc. You might have heard this. So bar means pressure, right? So bar remains iso means constant, okay. So that means pressure remains constant. So isobaric process, pressure remains constant. So if pressure remains constant, then the pressure volume graph will look like this, right? Pressure versus volume graph will look like this. And then suppose initial volume is V1, final volume is V2, okay. Initial volume is V1, final volume is V2, the pressure is constant, pressure is suppose P, then how much would be the work done in this process? So work done can be very easily written in this process. Work done would be just equal to P multiplied by V2 minus V1, okay, because work done is equal to what? P dV, integration of P dV from V1 to V2, and pressure is constant, so you can just move the pressure outside. So work done is just equal to what? Final volume, P times final volume minus the initial volume, okay. And then you know PV is equal to nRT, so you can substitute that here. So P times V2 is nRT2 suppose, and P times V1 is nRT1 suppose, right? So initial temperature is T1, final temperature is T2 because volume is changing, okay. So then what will you get? Work done would be equal to nR times T2 minus T1, okay. Are this formally clear? Yes, no? So now for isothermal process, let's see the first law of thermodynamics. Okay, first law of thermodynamics says what? So delta Q is equal to delta U plus delta W, and delta U would be equal to 0. Why? Because U is equal to, we know it is CV multiplied by N times CV multiplied by T, and it is directly proportional to temperature. Okay, the internal energy is directly proportional to temperature. So temperature remains constant, means there is no change in internal energy. So all of the heat is utilized in what? Only work done, right? All of the heat is utilized in doing the work, okay. So heat is completely converted to work in case of an isothermal process, okay. So for isothermal process, delta Q is equal to delta W, right? So then now suppose dW is the work done for small change in volume dV, okay. So work done can be written as what? Work done can be written as PdV, okay. And then temperature is constant, so we know PV is equal to nRT. So pressure can be written as nRT divided by V, okay. Just take that volume on other side, so pressure can be written as nRT divided by V, right? So now this pressure will replace by nRT by V, we can replace it by that, and therefore the work done can be written as nRT divided by V multiplied by dV. So why did we do this? Just to take, here there were two variables, pressure as well as volume, okay. What we are doing is we are converting this thing from two variables to one variable. Why? Because we want to integrate it, okay. So we want to integrate it, that's why we are changing it from two variables to one variable, and the limits of integration are from V1 to V2, okay. So work done when the volume changes from V1 to V2 is work done from V1 to V2 of dW, okay. And we have seen that dW is equal to what? nRT divided by V multiplied by dV, because pressure we have replaced by nRT by V, okay. So this thing PdV can be written as what? nRT by V times dV, okay. And then nRT is constant because temperature is constant in this process, right? So therefore nRT is taken out, okay, because the temperature is constant. Then you integrate it from V1 to V2, right? So integration of 1 by V dV is what? It is natural log of V. The integration of 1 by V dV is just natural log of V, okay. So ln of V from V1 to V2, then you substitute V1 and V2, right, the upper limit and the lower limit. So it would be ln of V2 minus ln of V1. So the work done in the isothermal process is what? nRT multiplied by ln of V2 minus ln of V1, okay. So this is work done in isothermal process, right? Then this ln of v2 minus ln of v1, so we know this log of a minus log of b is what? Log of a by b. Okay, log of a divided by b can be written as log a minus log b, and therefore this, what is this thing? Log of v2 minus log of v1 means it is log of v2 by v1, right? Is this thing clear? This is nRT log of v2 by v1. Okay, everyone? All right, and then now this is natural logarithm, and the logarithm that we use in the log tables, it is generally the log to the base 10. So what we do is we convert this thing. Okay, formula we need to remember this one as well as this one, but we convert this thing from natural log to log to the base 10 by multiplying with this factor. Okay, so the 2.303 nRT, then this ln will be changed to what? Log to the base 10. The work done in this case would be equal to 2.303 nRT log to the base 10 v2 by v1. Okay, log to the base 10 v2 by v1. This thing is clear? Yes, no? Okay, and then since temperature remains constant, just 1 second. Oh, it's there. Okay, so since temperature remains constant, you have PV equals to nRT. So P1 V1 is equal to P2 V2. Okay, and therefore if you move V2 on this side and P2 on this side, you get V2 by V1 is equal to P1 by P2, right? And work done in isothermal process can also be written as nRT log of P1 by P2, right? Because V2 by V1 is equal to P1 by P2. Okay, because temperature is constant, that means PV is constant. So P1 V1 is equal to P2 V2, right? So V2 by V1 is equal to P1 by P2, and then you can substitute this thing over here and you get work done is equal to nRT log of P1 by P2. This is another formula. Okay, is this thing clear? If you take pressure versus volume graph, then you know that pressure is inversely proportional to volume because PV is a constant. That means pressure would be inversely proportional to volume. So if you plot the graph between them, right, if you plot the graph between them, so the graph will look something like this. Okay, so this is graph at 300 kelvins, this is graph at 500 kelvins, this is graph at 1000 kelvin of some system. Okay, so on all these graphs the temperature remains constant. So these graphs are known as isotherms. Okay, these graphs are known as what? Isotherms. Okay, so temperature remains constant, that's why these graphs are known as isotherms. Then now we know how to find out slope of a curve, right? So since PV is a constant here, okay, what is slope of a curve? It would be delta P by delta V, change on the vertical axis divided by change on horizontal axis, right? Slope of a curve is change on the vertical axis divided by change on horizontal axis. Right? So here what we do is we write this equation in differential form, or you can say you are applying the product rule of derivatives. So you keep first thing as it is, take derivative of second thing. Okay, so it is P dV plus you take derivative of first thing dP. Okay, then keep second thing as it is. So P dV plus dP times V would be equal to 0 because pressure times volume is a constant. Okay, and then you can move this thing on other side. So P dV would be equal to what? Minus dP times V, and then you move this volume on this side and dV on that side. So you will get P divided by V is equal to minus dP by dV, or dP by dV is just equal to minus P by V. Okay, so the slope of this curve, is what? minus P by V. This thing is clear? Yes, no. The slope of an isotherm would be equal to minus P by V, right? Now we can go back and we can talk about the slope of pressure volume curve in an isothermal process, isochoric process. So this slope is infinite. Okay, this slope is infinite. What about slope of this one? Slope of this graph is 0 because there is no change in pressure at all, okay, with respect to volume. So the slope over here is 0, slope over here is infinite, okay, and slope over here is what? Minus P by V, right? So then these two are very simple. There is nothing to remember here. These are, you can understand them. Okay, slope here is infinite, slope here is 0, right? Okay, this one just remember. All right, let's see next one, the adiabatic process. What is an adiabatic process? So the adiabatic process is the one in which there is no conduction of heat between the system to surrounding or from surrounding to system. Okay, there is no conduction of heat, right, between the system to surrounding or surrounding to system. That means suppose you take expansion or compression of this gas under the adiabatic condition. Adiabatic means there is no exchange of heat, so the system must be insulated from all sides. Okay, the system must be insulated from all sides, from this side, that side, that side, it should be insulated. Okay, so here delta Q is equal to 0, right? Delta Q is equal to 0. Okay, so either the system will do some work against the surrounding. So if system does some work against surrounding, then what will happen? Its internal energy would decrease. If surrounding does some work on the system, then what will happen? Its internal energy will increase, right? So system has some energy, it is not getting any support from the surrounding. Okay, no heat is absorbed or no heat is even given out, so therefore it has got some energy delta U. If it expands, system expands, that means it has to do some work. So if it does some work, means its internal energy would decrease because it is not getting any heat, any energy from the surrounding. Okay, and if this piston is pushed inwards, that means the system is compressed. Then what will happen? Surrounding is doing some work, that means surrounding is giving some energy. Okay, so internal energy of the system would increase. Are the two cases clear? Yes, no? Right? Okay, and for this process PV raised to gamma would be a constant. Okay, PV raised to gamma would be a constant, and we know that what is gamma? Gamma is the ratio of specific heat capacity at constant pressure to specific heat capacity at constant volume, or molar heat capacity at constant pressure to molar heat capacity at constant volume, right? The ratio of specific heat would also be same, but it is Cp to Cv. Okay, that is gamma. We have seen this in kinetic theory of gases, right? So then now here, so I have explained that thing on this slide, that see, yeah, so delta Q is equal to delta U plus delta W, and in this process delta Q is 0. Okay, delta Q is 0, so that means take delta W on one side, I mean keep it on this side, take delta U on other side, so delta W is equal to minus delta U. Okay, so if system does some work, what will happen? Its internal energy would decrease. Okay, there is negative sign. System is doing some work. Our delta W is what? Work done by the system. It would be positive when work is done by the system, that means there is expansion. It would be negative when work is done on the system, right? So if system does some work, then delta U would be this thing would be negative. Okay, work done is minus delta U, so its internal energy would decrease. If work is done on the system, then internal energy would increase. Okay, this thing is clear. In adiabatic expansion, U decreases, and in adiabatic compression U increases, because for expansion system has to do some work, okay, and for compression surrounding has to do some work on the system, so it is providing some energy to the system, right? This point is clear, everyone? Okay, good. So then now see, in this process what is constant? PV raised to gamma is a constant, okay, and therefore now if you want pressure can be written as PV raised to gamma is some constant K, suppose. Pressure can be written as that constant K divided by V raised to gamma, okay, and we know that work done is equal to PdV, and in which pressure is substituted as K upon V raised to gamma, right? Pressure is substituted as K upon V raised to gamma, okay. So then dW is equal to that constant whatever it is, okay, so that K upon V raised to gamma times dV, and then what would be the work done from changing the volume from V1 to V2? So just integrate that. K is a constant, you can move it outside, so integration from V1 to V2 of 1 upon V raised to gamma, okay, 1 upon V raised to gamma dV, right? This is 1 upon V raised to gamma dV. So that 1 upon V raised to gamma is written as V raised to minus gamma, okay, so it is V raised to minus gamma dV, and then you have, okay, integration of this using our regular formula, that V raised to n dV. What would be integration of this thing? V raised to n plus 1 divided by n plus 1, right? You get V raised to minus gamma plus 1 divided by minus gamma plus 1. That integration goes from V1 to V2. So then you substitute the upper and lower limits. So upper limit is V2, so it would be V2 raised to minus gamma plus 1, minus lower limit is V1, so minus V1 raised to minus gamma plus 1, okay, and this minus gamma plus 1 in the denominator you move outside, okay, so it is minus gamma plus 1 means it is 1 minus gamma, okay, so 1 minus gamma, and then what you do is you play a smart trick. Is, you know that PV raised to gamma is a constant, so when you multiply this K with V2 you write it as P2 V2 raised to gamma, okay, when you multiply this thing, because PV raised to gamma is constant, no, this constant is PV raised to gamma, right? So you multiply this thing with V2, then you write it as P2 V2 raised to gamma, okay. So what do you get from there? Then you have V2 raised to gamma multiplied by V2 raised to minus gamma plus 1, so this plus gamma minus gamma gets cancelled, so what remains is P2 V2, and in the same way you multiply this K with this term as P1 V1 raised to gamma, so that P1 with V1 raised to gamma multiplied by V1 raised to minus gamma plus 1, again this plus gamma minus gamma gets cancelled, and what remains is P1 V1. So finally doing all this you get simple formula for work done, that is P2 V2 minus P1 V1 divided by 1 minus gamma, okay. So work done in the adiabatic process is equal to P2 V2 minus P1 V1 divided by 1 minus gamma, right? And you can always make use of PV equals to nRT, and you can write this thing as nR times P2 V2 can be written as what? nR times T2. P1 V1 can be written as nR times T1. So nR can be taken out, so it is nR times T2 minus T1. This is the work done, right? So you need to remember just one formula, this formula, right? That PV equals to nRT you can use anytime, okay? So you need to remember just this formula, okay? That P2 V2 minus P1 V1 divided by 1 minus gamma. So is this thing clear, everyone? Yes, no? Alright, so nobody is going to ask us these internal steps, right, of this derivation or the earlier derivation, but what we need to remember is PV raised to gamma remains constant in case of an adiabatic process, okay, and work done is equal to this much. If work done is equal to this much, tell me what would be the change in internal energy? If this is the work done, what would be change in internal energy? Anyone? In the adiabatic process? Yes, of course, negative of this. Very good. Okay, so change in internal energy would be just equal to, okay, delta U is just equal to what? This denominator, just change it to gamma minus 1. Okay, change the denominator to gamma minus 1, right? Okay, so I have written it 2-3 times that work done is equal to what? Change in internal energy. So this is an adiabatic process. And then, okay, so let's compare the work done in thermodynamic processes, right? So this is isochoric process, there is no work done. Isobaric process, okay, these are except for this isochoric, these are all expansions because volume is increasing, right? So in isochoric process there is no work done. Isobaric process, work done is maximum. Okay, remember this, work done in isobaric process is maximum. Okay, then comes the isothermal process, then comes the adiabatic process, right? The work done in isobaric process is maximum, then comes the isothermal, then comes what? The adiabatic process. Okay, is this in clear, everyone? So then let's talk about next topic. Okay, so that is the heat capacities. All right, so molar heat capacities. Now what is heat capacity? We know that. Okay, molar heat capacity is amount of heat absorbed by a substance. Okay, amount of heat absorbed by a substance per unit, per mole of substance per degree change in temperature, per degree rise in temperature. Okay, so that is the molar heat capacity. Okay, amount of heat absorbed by a substance per mole of substance per degree rise in temperature is the molar heat capacity, right? So then in case of isothermal process, what is change in temperature? The change in temperature is 0, we know. So if you put 0 in the denominator, what would be the molar heat capacity of this process? So in this process, the molar heat capacity is infinite. Okay, molar heat capacity of an isothermal process is infinite. This thing is clear, everyone? Okay, all right. So then in case of adiabatic process, so what is adiabatic process? In the process there is no heat exchange, is called as an adiabatic process. So if there is no heat exchange, means delta Q is equal to 0. If delta Q is equal to 0 means C would be equal to 0, right? So in case of adiabatic process, the molar heat capacity or specific heat capacity is equal to 0, right? The specific heat or molar heat capacity is equal to 0 in case of an adiabatic process. Very simple. Okay, then let's come to the next process, which is isochoric process. So what is an isochoric process? So in which the volume remains constant. So if the volume remains constant, then there is no work done, right? So let's see, let's write C is equal to, that is the molar heat capacity, and we are putting suffix V because it is at constant volume. Okay, so we had seen this thing in last chapter. Cv is what? The molar heat capacity at constant volume. So isochoric process means the volume remains constant. Okay, so then you have delta Q divided by N delta T. This is just definition. And then delta Q can be always written as delta U plus delta W. Okay, it can be always written as delta U plus delta W. And since volume is constant, delta W is equal to 0, and therefore it is just equal to what? Delta U by N delta T. Okay, so this implies, since delta W is equal to 0, this thing implies that CV is equal to what? Just delta U divided by N delta T. So suppose change in internal energy of some system is given, or the amount of heat absorbed is given, okay, both are equal because the volume remains constant in this process. So Cv can be just written as what? Delta U divided by N delta T, because delta W is 0, and then you can move this N delta T on other side and you can write the change in internal energy is just equal to what? N times Cv delta T. Okay, this thing is clear, everyone? Yes, no? Right. Okay. And this is isochoric process. Then last one is isobaric process. So in isobaric process, what happens, that Cp is equal to, okay, C is equal to delta Q divided by N delta T, the same formula, but here delta Q is written as delta U plus delta W, right? It is equal to delta U plus delta W, but here the volume also changes, and that's why there is some work done too, okay? And then delta U can be written as this thing, right? Delta U can be written as N times Cv delta T. You can write it here. Delta U is N times Cv delta T, and delta W is P delta V, okay? Delta W is P delta V, delta W is P delta V, which can be written as, see, PV equals to nRT, so this thing can be written as nR delta T, okay? It can be written as nR times delta T. What we have done is, we have written delta W as nR times delta T. This thing is clear? Yes, no? Okay, or do I need to explain it? Okay, that's clear, right? We have seen that earlier too. Okay, so delta W is equal to nR delta T. So here delta T and delta T gets cancelled. You can cancel out n also, and you get Cp is equal to Cv plus R. Okay, so this is the Mayer's relation that we saw in the last chapter too. But Cp is equal to Cv plus R, or Cp minus Cv is equal to R. Okay, and one more thing, that you can just flip this equation. You can just rewrite this equation in this way, that delta Q is equal to Cp times N delta T. Okay, so in case of an isobaric process, delta Q can be written as what? Cp times N delta T. This thing is clear? Okay, all right, good. So then let us see this question. So if Cp and Cv denote the specific heat per unit mass of an ideal gas of molecular weight m, then Cp minus Cv, these are specific heat per unit mass. So option B. All right, careful. This is specific heat per unit mass. It is not molar heat. Okay, so what is this thing? The Cp, I am writing small cp. It would be equal to what? This amount of heat absorbed, okay, per unit mass per degree change in temperature. It's specific heat capacity, right? And what is molar heat capacity? So let me write just small c. Molar heat capacity is amount of heat absorbed per mole, okay, per degree change in temperature. So then what you can do is, you can divide 2 by 1. 2 by 1 will give you this thing, but C divided by small c. Small c is the specific heat, and this is molar. Okay, this thing is molar. All right, so then this thing will get cancelled out, this thing will get cancelled out, and I want to divide 2 by 1. So divided by that is multiplied by its reciprocal. So what remains is 1 by m. You are dividing by 1 by m, means you are multiplying by m. So m divided by small n. Okay, what is this thing? M is the total mass which can be written. Okay, total mass can be written. So small capital C by small c is equal to, total mass can be written as number of moles multiplied by mass of 1 mole, and you have that thing divided by n. So that is equal to molar mass. Okay, so you have C, capital C is equal to small c times m, or small c is equal to capital C divided by m. Okay, so now you tell me what would be Cp by Cv. So you know Cp minus Cv is equal to R. Okay, so what would be Cp minus Cv? It would be R divided by m, right? Yes, no? Everyone? All right. So actually we had seen this expression, okay, this expression itself, that specific heat is equal to what? Molar heat divided by molar mass. So you need to remember this expression, okay, and then this won't take any time, right? We had seen this expression in last chapter. Okay, so it is option C. This is clear, everyone? Right? Good. Then it's 8:50. Anyways, so let's see very small question, some very small questions. In thermodynamic process, which of the following statements is not true? In an isochoric process, pressure remains constant. Okay, is it true, not true? Okay, this is the answer, right? Yes, no? Isochoric process, volume remains constant, so we don't even need to check the other options, but let's check. In an isothermal process, the temperature remains constant. This is correct. In adiabatic process, PV raised to gamma is constant. This is also correct. In adiabatic process, the system is insulated from surrounding. This is also correct, right? So in isochoric process, pressure remains constant is incorrect. Okay. Let's see this one. Two cylinders A and B of equal capacity are connected to each other via a stopcock. Okay. A contains ideal gas at standard temperature and pressure. B is completely evacuated. The entire system is thermally insulated. Entire system is insulated. The stopcock is suddenly opened. The process is. Tell me. Option B, adiabatic. Everyone? So this is A, this is B, and there is a stopcock between these two here, right? And what is given? That A contains ideal gas, so A has ideal gas, and B is evacuated. Okay, this one is at standard temperature and pressure. B is completely evacuated. There is nothing in B. Entire system is insulated. Entire system is insulated. Okay, so this itself tells us that it is going to be an adiabatic process. Okay. All right. So this one is from NEET 2020. The stopcock is suddenly opened. The process is. Okay. So they are not even asking what will happen if the stopcock is opened. Okay. If it is opened, what will happen? The gas will just expand. Right. It will enter B. Anyways. So then what will happen to temperature? Can you tell me? All right. So temperature will decrease. You can just claim that temperature will decrease in this case. So an ideal gas goes from state A to state B via three different processes as indicated in the PV diagram. This is 1, 2, 3. Okay, if Q1, Q2, Q3 indicate the heat absorbed by the gas along three processes, and delta U1, delta U2, delta U3 indicate the change in internal energy along the three processes respectively, then Tell me, first of all, tell me what would be change in internal energy along three processes. It would be same, it would be different. There can be a question just like this: what is change in internal energy along three processes? Is it same? Is it different? So delta C, U is a state variable, no? We have seen this state variable and path variable, right? So if they ask about change in U, if they ask about change in P, change in V, change in temperature, then it will be same, right? So delta U will be same. So either it is option 1 or it is option 2, right? Delta U is same. So then now let's go back here once again. Suppose pressure and volume here are P1, V1. Pressure and volume here are P2, V2. Okay. So it changes along these three paths, 1, 2, 3. So here, see, the graph would be like this. Here the graph would be like this. Okay. I mean, for first case, graph would be like this. Second case, graph would be like this. And in third case, the graph would be like this. Right. It's like this. Okay. So then, in first case, the work done would be more because area under the curve would be more. Area under PV graph would be more. So work done would be more compared to that of second case, right? Compared to that of third case. So delta W1 is greater than delta W2 is greater than delta W3, and then we know that delta Q is equal to what? Delta U plus delta W. Delta U is equal in all three cases. That means if work done in first case is greater than that of second case, it is greater than that of third case. That means delta Q1 must be greater than delta Q2. Okay. Oh, delta Q2, and it is greater than delta Q3, right? This thing is clear? Yes, no? Everyone? Okay, so it has to be option A. It has to be option A. Okay, good. So now we'll stop here. Okay, and other questions and all we'll see tomorrow.